So we made it, question 100. If you've come this far, then well done. I've got my party hat on specially. Let's have a bit of a celebration at the end of this one. So here's the question then. And the first thing is to draw a diagram showing all of the forces. So I'm going to look at the force on particle B first. B has got a mass of 7 kilos, so the force of gravity is 7g. And then that will induce tensions in this string. Now this string here going from B to C is a single piece of string. So if we assume that the string is light, then the tensions in all of those, the whole length of that string will be the same. So I've got the tensions at both ends of this section of the string, tension at both ends of this section of the string, and like I say, if that is a light string, then all of these tensions will be the same as each other. I'm going to call them all T1. So then I'm looking at particle A. A has got a mass of 3 kilos, so it will have a force of gravity of 3g. And looking at the tensions in the string, I've got tensions at both ends of this part of this string and both ends of this part of this string, and it's a continuous string. And if we again assume that this string is light, then all of those 4 tensions will be the same. I'll call them all T2. And I have to say T2 because I don't think, I'm almost certain that the 2 tensions will be different to each other. They're not the same tension. Now I have got force of gravity on C, and I've got a reaction from the table as well. I could draw those forces on, but to be honest, they're not going to affect the movement, the acceleration of C, because C is accelerating in that direction. Let's look at the accelerations now. So each of these objects is accelerating with the same acceleration, that is, if the strings are inextensible, but they're all accelerating in different directions. So I have to look at the equation of motion, F equals ma, for each of the particles separately. So looking at B to start with, I've got the resultant force on B. We've got 7g going down and we've got T1 going up. So the resultant force is 7g minus T1, and then that equals the mass, which is 7 times A. So that's the equation I get when I look at all of the forces, the equation of motion, Newton's second law, on B. Now I'm going to look at C. Or am I? Hang on a minute. Yes, I am going to look at C. And here I've got the resultant forces T1 on this side minus T2 on that side. So I've got T1 minus T2 equals mass times acceleration. The mass of C is 5 kilos. So there's my second equation. Now I'm going to look at the particle A and all of the forces on A. And here A is accelerating upwards, so I'm taking T2 minus 3g equals 3a. So now I have these 3 equations. I'm trying to solve them simultaneously. The easiest way of doing that is to simply add all of these 3 equations together. And what will happen then is that this T1 and minus T1 will cancel. The T2 and the minus T2 will cancel, leaving me 7g minus 3g, which is 4g, and here 15a. So 4g equals 15a. If I take g as 9.8, then that's my figure for A. Then I can pop that figure for A back into this equation, for example, to find T1. So T1 is 7g minus 7a. So when I put the figure for A in, I get T1 is 50.3 newtons. I can put my figure for A back into the third equation here. So I get T2 is 3G plus 3A. Putting the correct value of A into there gives me T2 is 37.2 newtons. So we can see that the tension in T1 is much greater than the tension in T2. So there we are. Have we finished? We've found the acceleration of each mass. We found the tension in each string. What properties have we assumed each string possesses? Well, we've assumed that they are light, which means that we don't have to include the masses of the strings in our calculations. And as I mentioned before, the tension is constant along the length of each of the strings. We've also assumed that the strings are inextensible, which, as I mentioned, is helping us to say that all of the particles have the same acceleration. So that's the answer to the question.